Well, a warm welcome to anyone joining. Thank you for being here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a problem in exponential functions. Again, just like a previous video. But this time we're going to be looking at exponential erosion, or I guess we can call it exponential decay. You'll notice that we still have an exponential component here. That is some base number, in this case it's e, and e is being raised to this power, sorry for the messiness, but it's being raised to this power of negative 0.05t. In fact, let me move this just a little bit. That makes it look a little bit clearer, yeah? Because there's a negative on the exponent, this equation models something which is decaying. It is decreasing over time. Remember that exponential growth looks something roughly like this. Well, exponential decay is going to have a reflection over the y-axis. So if we were to flip that graph over this vertical line, what would we end up looking at? We would end up looking at the decay, which kind of goes like that. It gets smaller and smaller over time, right? That's kind of what's going on. I don't want to spoil too much, but you should think about exponential decay as sort of a reflection of exponential growth. That's sort of what's happening. I keep hitting this zero boundary. That's a little bit better. I'm not hitting it that time. So go ahead and read the problem. Give yourself about, 7 or so minutes to figure this out on your own first. And then when you're ready, you can join back. See how we did it here. Okay, let's get started. So this is about a chemical solution that is being neutralized exponentially. They're somehow removing its strength. The concentration C of T is in milligrams per milliliter. That's not too important, but that's just telling us that whatever substance it is that they're trying to remove or neutralize is being measured in milligrams per milliliter of the solution. A solution is just like a liquid mixture, basically. And we have t as time, that represents the minutes. Here is our equation. So we're going to start off with part A, very simple. What is the initial concentration of the solution? Well, this is an application of the mathematical concept. What is the initial value? If we can find the initial value or locate the initial value of an exponential function from the equation, you'll know that that's going to be located right here. It's going to be 80, and let's see why by plugging in the value 0, because the initial value or the initial concentration would happen at t equals 0 minutes has passed by. That's going to give us 80 times e to the 0 power, because 0 times anything in that exponent is going to be 0. So we have 80, remember that anything to the 0 power, other than 0 of course, is 1. So this is just 80 times 1. And that gives us a total of, indeed, 80 milligrams per milliliter. All right, very easy to just plug in a value, and really we didn't have to plug in the 0, like I mentioned. You can identify that this is where the initial value is located, and that will take care of things for you. But now for part B, we're going to have to solve an exponential equation. It says, when will the concentration drop below a certain amount? So this amount, you might recognize the units, milligrams per milliliters. Remember, that was used to describe the concentration. So if they give you a value that's with that same number, or the same units, milligrams per milliliter, you can be sure that they're giving you a value for C, and the fact that they're asking when, that means they're looking for T. So you need to find / solve for T. Okay, so let's do this by using what they gave us, 7.5. This will certainly require a calculator. 7.5 equals, pardon me, 80 times e to the negative 0.05 t. The first thing we're going to do is divide both sides by 80. We need to get the exponential portion by itself. And solving this exponential equation is the same procedure as solving the exponential equation in the previous video, the only difference being we have a negative in the exponent this time, so our result is going to somehow be different. Alright, let's use a calculator for this. 7.5 divided by 80. Well, it does divide decently if you know your sixteenths really well. But anyways, this is approximately 0.09375. And this is going to be equals to e to the negative 0.05t. Now here's where what we do is a little bit different than what we did last video, is that we're going to take a specific log of both sides in this case. We're going to use ln, not just because it's natural, haha, good joke, but we're going to use this specifically because we have a base of e, and ln of e cancels out. So this is literally just going to be equals to negative 0.05 t. And that is quite easy to deal with now. We just have to divide both sides by negative 0.05. And you might think that that's going to make our time negative, but it's not. Because if you take a log, the natural log of 0.09375, you get a negative value. So then when you divide by a negative 0.05, you actually get that t equals about 47.34. And this is in minutes. So that's how many minutes it's going to take for the concentration of this chemical solution to drop below 7.5 milligrams per milliliter. So you can imagine this being effective for, I don't know, like giving a time for how long it would take to maybe remove a poison from the body or something. If we had an exponential equation which accurately models the situation. Could be effective, if it tells you, okay, it's going to take 47 minutes to get the concentration down to a certain level. This could even be true for certain heavy metals or toxic metals in the bloodstream. Very interesting applications for this kind of situation. Okay, now part C, find the average rate of change between these two times and interpret your answer with some words or thoughts or ideas. So first we have to find this average rate of change, C30, minus C10, which is the concentration at 30 minutes minus the concentration at 10 minutes, divided by 30 minus 10. So this is going to be 80 times e to the 30 times negative 0.05. Should be pretty easy for you guys to figure that, right? It's going to be negative 1.6. Oh, sorry, times 30. 1.5, silly. And then we're going to subtract 80 times e to the, plug in a 10, and we get negative 0.5. All over 20. Now, of course, we're going to need a calculator for this because those powers of e, any powers of e, are not very nice for us to do by hand. So 1.5, make sure you use a negative power. That's for the e, and multiply it by 80. So we have 17.85 roughly minus 48.52. I think that's a good estimation there. Over 20. So we're going to subtract these. And of course, that's going to give us about negative, 30-ish? 31? No, 30.67. Over 20. And so this is just going to give us negative 1.5. Let's call it 3. Maybe 4. I'll call it 3, 4. And this is in milligrams per milliliter. So that's how many milligrams per milliliter we're going down per minute. Okay, so the interpretation is that at this time, we know it's not decreasing the same amount every moment, but the average that it's decreasing is about 1.5 milligrams per milliliter each minute. So you can say comfortably in about 20 or 30 minutes, you'll have removed like 35 to 45 milligrams per milliliter of concentration. These are useful things, especially if you're going into the medical field. We want to sketch a graph and then interpret the end behavior over time. Now, I kind of hinted at that, but I do want to put some accurate values on the graph. I want to put 80 because that was the starting amount. And then I want to put a couple of these amounts that we had at 10 minutes. We still have about 45, or was it 48? Sorry. It was about 48.5. We're going to say that happened at 10 minutes. And then we know it's at like 17.85 way later at about 30 minutes. And then we also found on an earlier part that it would take about 47 minutes, 47.3 minutes, I believe it was. Yeah, 47.3 minutes for it to get below a concentration of 7.5 milligrams per milliliter. So we have a decent exponential decay. We have a decent little skeleton to use, you know what I mean, to help follow and more accurately draw this. Now, what can we say in the end behavior? Well, you see that as time goes on, it's going to balance out. You're never going to have negative concentration, and you're also not really necessarily going to have 0.000 concentration. You might always have a tiny little bit of that stuff lingering. So we can say, as t goes to infinity, c of t, it does approach 0. We're not going to say that it equals 0 because we can't have time be infinite. We can't go out to infinite time and see what happens there. But we see that there's this trend happening that as we get closer to forward in time even more, the concentration gets smaller and smaller towards 0. Okay, so this is an interesting application that you would see in like a life science or biological sciences class. Keep sharp with your exponentials because they come up in pre-calculus and they come up in calculus as well as science applications. I think that's enough blab out of me. I will catch you guys next time.